SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustion. Today we are going to start a new module, that is module V, fifth module, and the title of this module is Combustion and Thermochemistry. So from now onwards we will move towards the combustion part of this course, and we will see how our understanding in thermodynamics are helpful for combustion studies. This combustion is very vital in our day-to-day life, and in fact it is in existence since human civilizations. So the very basic intention for this module is to introduce the thermodynamic concepts in combustion applications. So in this module we will have 4 important lectures. The first one is thermodynamic considerations of combustions. Here we will be discussing about fundamental aspects of combustion and various terminologies that are used while dealing with the combustion studies. Then we will apply the conservation of energy for reacting systems. The word reacting means, that means there is a chemical reaction that takes place when combustion happens. We will try to see how our understanding of energy conservation will be useful for chemical reactions. Then we will try to introduce some important parameters which are very familiar in the combustion studies. First thing is adiabatic flame temperatures, then entropy. Of course, entropy we have used in our thermodynamic course, but how that entropy is a important phenomena which will decide the direction of chemical reactions. Now, in addition to this, we have another parameter, thermodynamic parameter, which we have introduced in module 3, which is Gibbs functions, and here we will see that how Gibbs function finds its applications in reacting systems. In the last lecture, we will be talking about the products of combustions and effective energy utilizations. Means that during a combustion process, by considering the constituents of combustion products, we can predict whether we have effectively utilized the fuel's energy or not. Now, if not, then what is the methods in which we can effectively use the energy utilizations during a combustion process. So, this is about overall introduction about the module 5, that is combustion and thermochemistry. Now, we will start the first lecture on this module, that is thermodynamic considerations of combustions. So, in this lecture, that is we are in the lecture number 19, that is overall lecture number, and first lecture of module 5 is the thermodynamic considerations of combustions, where we will be dealing with the combustion fundamentals, some terms like stoichiometry, equivalence ratio, products of combustions, and we will see that how thermodynamics properties can be evaluated for a reacting system. Now, let us start the first segment, that is combustion fundamentals. As I mentioned that combustion is in existence since human civilization, and in fact it is one of the important ancient discovery. So, basically during that point of time, people used to think of fire of woods, but in reality what happens during the fire process, there is a fuel and there is oxygen, and as a result we have the heat that is going to be generated. In fact, till today there is a self-sustained heat release mechanism that happens in the sun. So, if you look at sun's viewpoint, you can see that it is the infinite source of fuel which keeps on burning, and because of which we are in the receiving end in terms of light. And of course, during this combustion process there is some exhaust emissions which might have occurred in the deep space or in the vicinity of sun, and many times we call this as a solar storm. Okay, so we call, and this they are nothing but the exhaust that comes out from the during self-sustained combustion for which it happens in the sun. This is just to give the importance of the topic combustions, and in our viewpoint we will view it as a chemical reaction between a fuel and air. So, fuel and air means it is an oxidizer. So, when they react we get a combustion products. So, in totality we say there is some reactants and there are some products. So, by definition one can say rapid oxidation to generate heat or light or both, or slow oxidation accompanied by little heat or no light is regarded as the basic definition of combustion. Now, when you say this combustions, it can occur in a flame mode or non-flame mode. We all know that when the combustion happens in engines, SI engines or CI engines, we can say there is flame is generated and that keeps propagating, that is in the SI engine combustions, whereas in the diesel engines there are auto ignition of fuel, and because of this we get a diffusion flame in the CI engine combustions. Then moving further to the another side of this combustion process, in reality what happens? Basically fuel and oxidizer they mix, they form as reactants, and when there is an ignition then what happens? Fuel is burnt. So, by fuel is burnt, what do you mean is that internal energy for the fuel is broken. So, in totality what we can say that there are bonds, that is that happens when you consider the diatomic species or monoatomic species. Now, when you consider this a monoatomic species, we will have a translational kinetic energy. When you look at the diatomic species, the internal energy results from the translational together with energy from the vibrations. So, basically speaking, by adding through this combustion process, we are trying to break the chemical bonds. Now, as a result we get the heat release that we realize. So, ultimately what fuels that we are been using till today, they are typically hydrocarbon fuels, and by using this fuel energy we are producing the power. So, our main intention of this combustion studies is to look at these chemical reactions, its dissociation process, studies this thermodynamic analysis when such a combustion combustion takes place. And this fundamental principle will also allow us to determine the equilibrium compositions of mixture. The next important topic that we are going to discuss is the reactants, products and stoichiometric coefficients. We mentioned that during a combustion process there has to be some reactants and there has to be products. For example, in a hydrogen combustion, that means when hydrogen and oxygen they mix, we get water, and during this process it is a chemical reactions. So, what we say, the reactants consist of hydrogen and oxygen, products is the water. So, we got the definition, means what is reactants and what is products. Now, when you write these things in the equation form, we call it as a chemical equations. So, all the combustion reactions are expressed in terms of chemical equations, and the way we say that a mass balance is applicable for thermodynamic analysis, we also have the mass of reactants and mass of the products should be equal. And if you look at this particular reaction, hydrogen and oxygen, it gives water. So, the number of species that are involved here is hydrogen, oxygen, and you can see that we have to see that there is a number of hydrogens which is there in the reactant side should match with the number of hydrogen in the product side. Also, hydrogen may not exist in its own form, but it has mixed with oxygen to form water, but this hydrogen exists in water in the product. So, what it says is that total mass of each chemical element of the products must be same on both sides of the equations. But however, one important thing is that if you talk in terms of moles, the moles may be different. If you look at here, there is one maybe you can say 1 kilomole of hydrogen, half kilomole of oxygen, and when they mix, so the total kilomole will be 1.5 kilomole, but when you see the product, it is only 1 kilomole of water. So, the coefficients, that is stoichiometric coefficients, that means what we say is that this, when you in a balanced chemical reactions, the stoichiometric coefficients, they are not same. That means in this equation 2 kg is the stoichiometric coefficient for hydrogen, 16 kg would be the stoichiometric coefficient for oxygen, but if you say 2 kg and 16 kg, they are going to match as 18 kg of water. Apart from this, then we have another parameter which is fuel. So, fuel till date we have fuels which is available in the form of hydrocarbon fuels. Now, when I say fuels, they are nothing but the mixture of combustible chemical elements, mainly carbon, hydrogen, and they both are called together as hydrocarbons. Then we have also sulfurs, but however, the sulfur has least energy, least contributor in the energy productions, but it is the main source of pollution and other corrosing environment. Now, when I say complete combustions, so fuel must burn with oxidizer. So, for this thing there will be a complete combustions. It can takes place when all the carbons in the fuel is burned to carbon dioxide. That means, during a complete combustion process, the carbon in the fuel should form carbon dioxide, the hydrogen should form water, sulfur will form sulfur dioxides. So, this is how we have to get, if not then it is a incomplete combustion. So, in totality we try to avoid the incomplete combustions. Now, coming back to the fuel. So, fuel is nothing but a combustible substance which mainly contains hydrogen and carbon, commonly known as hydrocarbon, and they exist in 3 phases. First is in liquid phase in the form of gasoline, diesel, kerosene, fuel oil. So, they are nothing but the liquid hydrocarbons derived from the crude petroleum products through distillation and cracking processes. Then we also have fuels in the gaseous form. One such example is methane, where gaseous hydrocarbons are obtained from the natural gas through certain chemical process. And we also have solid hydrocarbon fuels, which is nothing but the coal. So, the fuels are available in the liquid, solid and gaseous form, and mostly till now we are very used to it, with respect to liquid fuels, that is gasoline, diesel and kerosene. Then moving further, fuel as a whole it cannot burn, so we need oxidizer. So, that means for every reactions oxygen is required for a combustion process. But what happens is that the usage of oxygen is not possible in combustion applications. Usage of oxygen means, I mean it is a pure oxygen. So, pure oxygen deriving from atmosphere is very critical task, but normally what you do, we use air as a mode of supplier of oxygen. So, if you look at the composition of dry air in terms of mass fractions, it is nitrogen is close to 78.08%, oxygen is 20.95%, argon is 0.93%, carbon dioxide is 0.03% and rest of the other gases is 0.01%. Now, if you see the major constituents of air is nitrogen and oxygen. So, for the combustion study, a effective way, that means instead of taking all these components, all other components like argon, CO2 and which are very minor components, they are merged with nitrogen. So, for the combustion analysis what we study, what we say is air consists of nitrogen and oxygen, and in terms of percentage we can write like this, it is contains 21% oxygen and 79% nitrogen on molar basis with molar ratio of 3.75, which means if you want to take 1 mole of oxygen from air, it is always accompanied by 3.76 mole of nitrogen. So, although you are using this nitrogen gas and this in a effective chemical reactions, the nitrogen becomes inert. That means, nitrogen has no role during the combustion process. So, basically speaking, if you look at here in a actual combustion process, as I mentioned, or complete combustion process, all the fuel should burn, that means carbon should come to carbon dioxide, hydrogen should come to water to form water. So, in a complete combustion process we will get CO2 and water. Now, in same reaction when you view with air, we can say in a complete combustion process we get same CO2 and water, but what remains intact or inert is the quantity of nitrogen gases in the reactant and products, they remain intact. So, in a complete combustion process it is felt that nitrogen does not undergo in the chemical reactions or does not participate, although it is given, but it does not participate in the combustion process. So, it is regarded as inert, as a inert gas for the combustion process. But what happens, although it is present, but what happens during the chemical reactions, the temperature goes off, and this when there is a temperature goes more than 1000 or 1500 degree Kelvin, then what happens, the nitrogen tries to break, bonds of chemical, that means nitrogen gas tries to dissociate. So, when it dissociates during this process, it is more likely to react with the oxygen and to form the compounds like nitric oxide, nitrogen dioxide, and these are nothing but the source of air pollutions. That means, they are essential culprits for the combustion process. This needs to be avoided, and that why this happens, because we do not get pure oxygen. We do not have pure oxygen during a combustion process. So, we have to be very careful while dealing with this nitrogen and whether it, when it reacts, what type of compound it forms. The next important segment in the combustion process is a stoichiometry. The word stoichiometric means it is a parameter that is very common, and basically the reactants in a combustion process consist of fuel and air. And when I say a complete combustion process, that means fuel requires adequate amount of air or exact quantity amount of air for a complete combustion process. If this happens, then we call it a stoichiometric conditions. That means, in a complete combustion process, stoichiometric air has to be supplied. So, for that reasons, there are two parameters that pops up. One is air fuel ratio and the fuel air ratio. Air fuel ratio in a chemical reaction is the ratio of the amount of air to the amount of fuel, and this ratio also can be written either in mass basis or in the molar basis. Now, the minimum amount of air that supplies oxygen for a complete combustion of the fuel is known as theoretical amount of air, and many times you also use the theoretical amount of air, which is same as the stoichiometric quantity of air, or that means stoichiometric quantity of oxidizer is needed for a complete combustion process. When I say stoichiometric combustion, that means there is no free oxygen that appears. Now, when not necessarily that always a combustion process has to happen in a complete mode or stoichiometric air is being supplied. Now, if when the more than stoichiometric quantity of oxidizer is supplied, then the mixture is said to be fuel lean. That means, it is rich in air, lean in fuel. While supplying less than the quantity of stoichiometric oxidizer, it results fuel rich mixtures. Now, in a fuel rich mixture, always free oxygen appears. We will see later point of time where how the free oxygen appears in the products in a fuel lean combustions. Alternatively, when I say theoretical amount of air, we also call as percentage excess air. So, theoretical amount air and stoichiometric, they are same. Now, we say percent excess air, that means if I say 100% theoretical air, that means we are in the stoichiometric conditions. If I say 150% theoretical air, that means we have 50% excess air or oxidizer. Now, if I say 80% theoretical air, which means 100% is actual theoretical air, but if you are putting air for stoichiometric conditions, when I say 80% of theoretical air, which means it is equivalent to 20% deficit air, or we say the fuel is rich. So, it is a rich fuel or lean fuel, they are very common, which we have been using during our IC engine course as well in the basic thermodynamic course. So, how to quantify this? So, first number what we say air fuel ratio, which is AF, that is mass of air divided by mass of fuel. Now, for this mass of air, if you represent in terms of number of moles, molar quantity of air Na into Ma means molecular weight of air, divided by Nf into Mf, and when I put this Na by Nf, instead of air fuel ratio we say molar air fuel ratio, that means number of moles of air to the number of moles of fuel, into its molecular weight ratio Ma by Mf. So, this is how the relation between air fuel ratio on mass basis and air fuel ratio on molar basis, Af and Af bar, where Af bar is represented in terms of molar basis. Now, next parameter that we are going to discuss is the equivalence ratio. So, we already told about the excess air, deficit air. Now, during an actual combustion process, how do you take a decision which parameter we need to regulate. So, basically instead of talking about air fuel ratio or fuel air ratio, another parameter is defined, which is equivalence ratio, and it is the measure of fuel air ratio relative to the stoichiometric conditions. And we have discussed about the complete combustion process and incomplete combustion process. When there is a complete combustion process, it refers to a stoichiometric chemical reaction between fuel and air. Now, when you have incomplete combustions, it is a non-stoichiometric situations. Now, to define this non-stoichiometric situations, the equivalence ratio is chosen as the one of the non-dimensional parameters. In fact, its main advantage is that it says whether a mixture is rich in fuel or lean in fuel. The reactants form lean mixture when the equivalence ratio is less than unity, and when they form rich mixtures when they have equivalence ratio greater than unity. And the parameter that is used is phi, that is equivalence ratio, fuel air ratio actual divided by fuel air ratio stoichiometric, and when it is represented in terms of air fuel, it is air fuel ratio stoichiometric by air fuel ratio actual. And we also know what is the air fuel ratio, we also know what is the fuel air ratio. Air fuel ratio is Ma by Mf, fuel air ratio is Mf by Ma. Now, from this equation it is clear that when phi is less than 1, it is a lean fuel, which means oxygen remains in the product. If you look at these equations, methane air combustion in a lean fuel. Let us start with stoichiometric methane air combustions. If you see here, methane CH4 plus oxygen, and it is inert nitrogen, and here also this inert nitrogen remains as it is 2 into 3.76 N2, and the combustion product is CO2 and H2O. So, it is a stoichiometric methane air combustions. Now, I say now if it is lean fuel, that means rich in air. Rich in means it is 150% theoretical or stoichiometric air. So, 150% means that means 1.5 times higher. So, when I say 1.5 times higher, the air becomes 1.5 times higher. So, you have 3 O2 into 3 into 3.76 N2, and here when I make this reaction to happen, in the products we have CO2, water, nitrogen, but what lands up is that free oxygen which is available in a lean fuel situations for a methane air combustions. Now, another scenario we can have the rich fuel. Now, when you have rich fuel, we will have carbon monoxide and onboard fuel in the products. Let us see how it happens. If you consider the stoichiometric reaction of isooctane air, that means it is another fuel. Isooctane is the fuel, air is the oxidizer. If you do that, and in a balanced chemical reactions, it says that C8H18 plus 12.5 O2 plus 12.5 into 3.76 N2 will give 8 CO2, 9 H2O, 12.5 into 3.76 N2. But what we require is rich fuel, that means rich fuel means 80% of stoichiometric air, that means it is air in deficit. So, if that is the case, the 12.5 becomes 10, it is 20% deficit, and nitrogen also will have 10 as a stoichiometric coefficients. And then once you do this, then we can have a balanced chemical equations that forms CO2, water, nitrogen, and this here we have carbon monoxide as well as we will have unburnt fuels that remains, and fuel did not get sufficient quantity of air. An ideal situation would be phi is equal to 1, which refers to a stoichiometric fuel, which means at this situation we will have release of maximum energy from the fuel. Okay. Now, next segment that we are going to discuss is the products of combustion. Till this point of time, we have seen fuel mixes with oxidizer to give combustion products. But what are the products that comes? And in an ideal situation, the products will be carbon dioxide, carbon monoxide, carbon dioxide, water and nitrogen. Now, that means this is a complete combustion to obtain a balanced chemical reaction. But what happens in an actual scenario, none of the combustion process is a complete combustion process. It is always will have incomplete combustions. So, to quantify, that means whether it is incomplete depends on the whether we are rich in fuel or lean in fuel, and in the parameters like NO, NOx, CO, all these constituencies are likely to be present. Now, to quantify such parameters, there are several devices that measures the composition of combustion products, namely Ostat analyzer, gas chromatograph, infrared analyzer, flame iodization detectors, and all these things they are reported as dry product analysis, and they are represented in terms of mole fraction. So, basically all combustion products, if you look at these products CO2, nitrogen and this thing except water, all products the analysis we do, we call this as a dry product analysis in terms of mole fraction. But what happens water, here the question mark that comes in, what happens to water? Now, this water depending on the temperature of the exhaust products, water may exist in a vapor form, or what happens if the vapor is exhausted to atmosphere, it gets cooled, and during this cooling process the water may form, vapor may turn back to liquid. So, when water vapor changes its phase to liquid form, so it has to pass through a temperature which we commonly use the word in psychromatics, which is called as dew point temperatures. So, initially the gaseous products of combustions, they are already at elevated higher temperatures, and when they are released or cooled to the atmospheric pressure, the water which was existed as a vapor from it changes its phase, and they are likely to condensate, and this condensation has to happen or has to pass through the dew point temperature, and this temperature depends at what partial pressures or how much at what partial pressures that water vapor exists, that we can find out number of mole fraction of that constituents. Okay. The very basic point is that when the vapors begins to condensate or liquid droplets are formed, they effectively create corrosions in the metal parts, duct pipes, all these things. So, this is the downside of the combustion process, that continuous exposure of water in the metallic parts leads to corrosion and further damaging of surface. The last segment of this part is to study the thermodynamic property analysis for a reacting systems. So, here the first basic assumption that we are going to make is that till this point of time, before this combustions, we have exhaustively discussed the multi-component systems and they are treated as an ideal gas mixtures. So, the reference line for the combustion study is that as if it is a mixture of reactants and products, and we have to find out the each constituents, their mole fractions, their individual parameters, and multiplied and we have to multiply that with respect to their respective mole fraction or mass fraction to get the effective thermodynamic parameters, like we can say they are like internal energy, enthalpy, entropy. And this analysis has to be, we have to recall it as an ideal, as a reference viewpoint, we have to recall them as an ideal gas mixture to calculate these properties. For example, if you say internal energy is the summation of the molar specific internal energy multiplied by the mole fractions for all the components, and same logic applies for enthalpy as well. Now, for entropy we have to use, there is similar philosophy is used, but entropy is calculated at temperature T and pressure, because it is a function of temperature as well as pressures. But here to calculate this temperature and pressure, people use the concept of absolute entropy, where we assign this reference value of given constituents at reference pressure P ref and temperature T reference temperatures. And as we did in the ideal mixture analysis, the reference value was taken as 1 atmosphere, reference temperature was 25 degree centigrades. So, the concept of absolute entropy is used to find the entropy of the ideal gas mixture. Okay, with this we have come to the end of this contents of the student lectures. Now, we will based on the lecture contents or whatever contents we have covered, we will try to solve some numerical problems. The first problem is based on air fuel ratio calculation or fuel air ratio calculation on molar and mass basis for a complete combustion process. And here we have used the word octane as the fuel. We have to calculate this air fuel ratio for a theoretical air situation, excess air situations, and when you are using the excess air, we have to find out the equivalence ratio. So, when such a problem comes, first thing you have to write two equations. One is balanced chemical reaction between fuel and oxidizer, other is unbalanced equations. Unbalanced equation means when we have excess air or excess fuel. So, it is a octane oxygen combustion. Balanced reaction, we can write as C8H18 is the fuel which is octane, and it has to mix with air. So, air means we do not know the coefficients. So, I will write it as A times O2 plus 3.76 N2. So, it will give you B times CO2 plus C times H2O plus d of N2. So, first thing we have to do balance. Balancing the components. Carbon, here you have 8 number of carbon, you have B. So, carbon we can say B is equal to 8. Then next thing is hydrogen. Hydrogen we have 18 number here, we have twice C. So, twice C is equal to 18, which implies C is equal to 9. Then nitrogen. So, balancing nitrogen we can say 3.76 times A here, nitrogen is D here. So, we can write is D is equal to 3.76 times A. Already we do not know A, so then we have to calculate the oxygen. So, we can write left hand side, it is twice, right hand side is twice B plus C is equal to twice A. So, we know C, we know B, we know C. So, this will give you A is equal to 12.5. When I say A is equal to 12.5, this will say D is equal to 47. So, the balanced reaction now becomes C8 H18 plus 12.5 O2 plus 3.76 N2, it gives 8 CO2 plus 9 H2O plus 47 N2. Then we are now in a position to calculate the mole fractions and as well as the mass fractions. So, before that, for this fuel we can write molecular weight of fuel, that is C8H18. C8H18 for fuel we will have 12 into 8. 8 times molecular weight of carbon is 12 and their number is 8. So, 12 into 8 plus hydrogen 18 into 1. So, molecular weight of fuel is 114. We all know molecular weight of air is 28.97. So, we are now in a position to calculate air fuel ratio on molar basis, that is 12.5 plus 12.5 into 3.76, that is number of moles of air in the and number of moles of air and number of moles of fuel is 1. So, this is 59.5 kilomole air by kilomole fuel. Now, if I calculate air fuel ratio, because we know air fuel ratio in molar form F bar multiplied by m of air and m of fuel. So, this number is AF, air fuel ratio is 15.1 kg air by kg fuel. Here it is kilomole, it is kg. So, this is how what happens is a stoichiometric conditions. Now, second part which we are going to study when we have 120% theoretical OR. So, that means this coefficient has to be increased by 20%. So, the reaction will now become C18 H18 plus, it is 1.2 times excess air. So, I can write this 1.2 into 12.5 into O2 plus 3.72 N2 3.76 N2 will give you B times CO2, we do not know this coefficient, C times H2O plus D times N2 plus E times O2. So, this coefficient needs to be calculated. So, we have now from these equations this reactant side all known parameters, product side we have unknown parameters. By repeating same principle, balancing the components, we can get like this: B is equal to 8, C is equal to 9, D is equal to 56.4, E is equal to 2.5. Now, after putting this, we rewrite this equation as C18 H18 plus 15 times O2 plus 3.76 N2 will gives 8 CO2 plus 9 H2O plus 56.4 N2 plus 2.5 O2. So, here air fuel ratio we can write F bar would be 12.5 into 1.2 plus 12.5 into 1.2 into 3.76 divided by 1. So, this parameter is for oxygen, this parameter is for nitrogen. So, this number will give you 71.4 kilomole air divided by kilomole fuel. Now, once we know air fuel ratio, we can write this air fuel ratio on mass basis, that is F bar into MA by MF. So, this number would be 18.15 kg air by kg fuel. Now, last parameter, what is the equivalence ratio? So, equivalence ratio phi we can write is AF by stoichiometric divided by air fuel ratio of actual. So, both the numbers we have we know stoichiometric value is 15.1 divided by 18.15. So, this is about 8.833. Other way to find out is phi is also equal to F bar stoichiometric by AF bar actual. This number will also lead to 0.833, which means phi is less than 1. Okay. Now, next problem is the data analysis for a methane air combustions. When this methane is combusted with air and we get the combustion products, and those combustion products consist of CO2, CO, O2 and N2 with their respective compositions. We need to find out air fuel ratio on molar and mass basis, percentage of theoretical air and dew point temperature. So, for this case also we say it is a methane A times CH4 plus oxygen B times O2 plus 3.76 N2. So, this is the reactant site and this is air and this is methane, and it reacts to form C times CO2, which is this, plus, and we know this C is 9.8 time point CO2 plus D times means 0.6 times CO plus 86.6 times N2 plus 3 times O2, and of course we get water. This water is C times, which is unknown, C times CO2, C times H2O. So, basically unknown are stoichiometric coefficients of methane, air and water. Known quantities are the molar analysis for CO2, CO, O2 and N2. So, we have to do the balancing of stoichiometric coefficients. And if it will result what? A as 10.4, B as 23.5, C as 20.8. Now, once we have this, then we are in a position to write this complete balanced equations, that is 10.4 times CH4 plus 23.5 times O2 plus 3.76 N2 will give you 9.8 CO2 plus 0.6 CO plus 86.6 N2 plus 3 O2 plus 20.8 H2O. Now, we have MCH4, that is methane 16, MAR 28.97. Then we can calculate air fuel ratio. AF bar is N number of moles of air, number of moles of fuel, and fuel we can say it is 10.4, which is here. Air is 23.5 into 1 plus 3.76. This number is 10.75 kilomole air by kilomole fuel. Then once we know AF bar, then we can find AF on mass basis, MAR by M fuel, and this number would be AF by into M air by m fuel. By putting this number we get it is 19.47 kg air by kg fuel. So, we get air fuel ratio on molar and mass basis, percentage of theoretical air. So, if it is a balanced chemical reaction, what would have been that CH4 plus twice times O2 plus 3.76 N2 will give you CO2 plus twice H2O plus 2 into 3.76 N2. Then in that case your AF bar would have been, which is stoichiometric value, N air by N fuel, that is twice times 1 plus 3.76 divided by 1, it is 9.52 kilomole air by kilomole fuel. So, percentage of theoretical air would be like AF bar by AF bar stoichiometric into 100. So, it is 113, that is 13% excess air. By putting this number 10.75 divided by 9.52. Third point is calculate the dew point temperature of the products if mixture were cooled to 1 bar. So, basically the products that water is forming dew. So, what is the mole fraction of this number? So, we can say water is available as component stoichiometric coefficient 20.8. So, we can say mole fraction of water vapor as 20.8 divided by 100 plus 20.8. So, this number is 0.172. Now, partial pressure of water vapor is by V into P. P is 1 bar. So, this number is 0.1744 bar. So, we know this partial pressure, and corresponding to this partial pressure we refer saturated pressure table for water, and this will give you temperature as about approximately 60 degree centigrade. So, means when these temperature products are cooled at 1 bar, water will form dew, and this dew point temperature is 60 degree centigrade at that partial pressure. So, this is how the problems are solved for you can see here, one is on stoichiometric situation, other is a non-stoichiometric situations. With this I come to the end for this lecture today. Thank you for your attention.